So the last portion of our lesson today is on pH curve, and this is a pH curve is basically a graph that shows the change of pH against the volume of alkali required to neutralize a known volume of acid. I can have the opposite as well, where I'm trying to find out the volume of acid required to neutralize a known volume of alkali. Okay, so our context over here is in the titration setup, titration process. And if you look with me at your theory book, here we see a setup of the titration process where I have the burette and sodium hydroxide is placed in it, and then I have a conical flask where a known volume of hydrochloric acid is placed in it. So this one is a fixed volume. So let's say this is about 25 cm cube, right? And I want to find out the volume. To find out volume of sodium hydroxide required to neutralize this volume of hydrochloric acid. Okay, so how can I find that out? I will actually need to carry out this titration process, and I will need to chart the change of pH as I add in more and more sodium hydroxide and find out when exactly is the point of neutralization of both solutions. Okay, so our the reaction that we're talking about here in context is neutralization reaction. So this is actually an alkali, sodium hydroxide, plus hydrochloric acid. I get sodium chloride, which is the salt, plus water. Okay, and we need to find, right, again, we need to find out the volume of sodium hydroxide required to neutralize the known volume of acid. So how do I know when exactly is the neutralization point, or the volume of sodium hydroxide required? So because it's a neutralization reaction, I will need the entire solution at the end of it to reach pH 7. So our endpoint must be pH 7, right? So this is when I know that the whole solution has been neutralized. And in the case of a graph like this, I am able to find out, using a graph like this, I'm able to find out what exactly is the volume of alkali required to neutralize the acid. Okay, so in order to get the change of pH like that, I can't just use a indicator like methyl orange. What I will need to use is a pH probe. So a pH probe will need to be put in here. So this is my pH probe. Sorry. So this is my pH probe. And this is usually connected to a computer that will chart the change of pH as I drip in more and more sodium hydroxide into the acid. So as the reaction start, you see that the pH changes from the acidic range, because I started off with hydrochloric acid. It will not have much change initially, and then it suddenly spike up, and then it reaches the pH of mostly alkali. So this one is when it is alkaline, right? And in this case, you will usually understand that this is when excess alkali has been added. And at the start over here, this is where it is acidic. So what I want is pH 7, right? So pH 7 is over here. If I have a graph like this, I'm able to interpolate across and then downwards to find out what is the volume of alkali required to neutralize this sodium hydroxide. So using a graph like this, I can find out, hey, this is the volume of NaOH, NaOH required to neutralize the volume of hydrochloric acid. Okay, so um, this point over here, where is pH 7, we call it the equivalence point. Or sometimes we call this the endpoint, of neutralization. All right, so these are some of the terms that you need to know with respect to a pH curve for the context of a titration setup. So going back to the slide, okay, you will, the other thing you will also realize is that the graph is logarithmic in nature. Is logarithmic in nature. What does that mean? It means that it is mainly it mainly has no change at the start, and then it will suddenly spike up like this and then remain having no change at the end. This is in contrast to a linear graph, right? A linear graph, on the other hand, is a straight line graph. So a linear graph will look like this, where it whatever things that I added in will cause a direct change as an effect. But you would realize that our pH graph is not a linear graph. In fact, we usually call it a S-shaped graph because it is S-shaped. Okay, so if I start off with the acid, it will begin at the bottom here. So this is if my start is an acid. If my start is an alkali, it will then have the other shape, right? Because at the beginning, the pH should be high if I started off with an alkali. So this is a S-shaped graph. And next time when you hear us talk about it this way, you understand that we are mainly looking at the pH graph. Okay, so yeah, so if you look at the self-check, look at the questions below. So based on the graph in the previous slide, it's pH directly proportional. Whenever you see the phrase directly proportional, it is actually talking about whether is it a linear graph or not, right? So they are asking, is the graph linear? So we went through just now, it isn't. Instead, it is logarithmic in nature. Okay, so that's why over here, how would you describe the shape of the pH curve? The curve is logarithmic in nature. Okay, the curve is logarithmic in nature. And then if I have a small volume of alkali added, the graph usually has little change. But near the equivalence point, so near the endpoint neutralization, the graph will increase sharply beyond pH 7. So once it passes the equivalence point, once it passes the end of the neutralization reaction, it will mean that I have added in excess alkali. So that's when it says over here, when excess alkali is then added, the graph remains horizontal because there's no more acid, right? So there's no more reaction. So that's why it shows the actual value of the alkali in the end. Okay, and so let's just complete this. So based on the graph below, complete the table with the corresponding pH values. So when there are no alkali added, when there's only acid, the pH is the one at the start over here. All right, so this is at pH 2. When 2 cm³ of alkali is added, so this is when you interpolate upwards, you'll notice that it is still having no change. It still has pH of 2. And similarly, all the way until when I reach pH 6. When I reach pH 6, and you interpolate it across, this is when it has a pH of 7.0. So similarly, you can continue and you get the rest of the values at 12.0 over here. Okay, so yeah, that is the portion for pH curve. So what have we learned today? What have we learned today? We have learned firstly the definition of an acid, that it must have hydrogen ions in the presence of water. Okay, we have also learned the definition of bases, that it is a substance that accepts hydrogen ions. We have learned the difference between the similarity and difference between a base and an alkali. A base is basically the insoluble, a base includes both soluble and insoluble versions of metal oxides and metal hydroxides, but the alkali is only the soluble version of the of a base. All right, so this is the soluble version. This can be both soluble and insoluble. So we can also call an alkali a base. We have also learned how to determine the nature of the solution based on the concentration of hydrogen ions versus concentration of hydroxide ions. So if I have more hydrogen ions, it's acidic. If I've got equal concentrations of both, it's neutral. If I've got higher concentration of hydroxide ions, it is alkaline. We have learned the colors of indicators, namely litmus, methyl orange, and universal indicator. And lastly, we have learned how to interpret a pH curve. So that's for the lesson for today. Please continue to go on to complete the questions that are in the SLS to check for your understanding. Okay, that's it. Bye.